So this is the definition of work. It's the magnitude of the force. And that's going to become really important. We got to understand that's a magnitude. It's the magnitude of the force. We could even put absolute values times the displacement in the direction of the force. And the displacement in the direction of force is also, it's not a magnitude, but it's not a vector either, because it's the displacement in the direction of force. It's not a magnitude in the sense that it can be negative, but it is not a vector either. And I'll show you what I mean in a second. But the point here, and this is the most important thing, is that work is not a vector. Work does not have a direction. If we look at the work done on the couch, you could say, I do work to the right. And the frictional force does work to the left. You could say that, but we can't actually. I mean, you could say, well, can't we say that? No, because work is not a vector. It's not a vector. It's a scalar quantity. It's a scalar quantity made up of magnitudes of vectors, right? This is the magnitude of the force times the magnitude of the distance in the direction shown. Okay, so that is just the definition. Work is a scalar quantity. Write this as a better formula. Let's take a slightly more arbitrary situation, a mass, and we're pulling it with some force, but it's displacing in some other direction, d, and there's some angle between the force and displacement. So this is just some arbitrary force and some arbitrary displacement. These are vectors, force and displacement, that have magnitudes of f and d by themselves without the vector sign. And so this could be, for example, it could be a box on the ground that we're pulling with a rope, so it's moving along the ground, but the pulling force is not along the ground, for example. Right? So what is the work done? The work done is the force times the displacement in the direction of the force. Let me also say that that definition, we will see in a second, is the same as the magnitude of the displacement times the force in the direction of the displacement. So in doing this definition, what I want to do is show that these two are actually the same thing. And it makes sense sometimes to think of one or the other, and you can think of either one. So let's just take the original one that I wrote down, the first one that I wrote down. Force times displacement in direction of force. So what does that mean? What that actually means is that we got to take the direction of the force, right? So we got to put an axis along the direction of force and take the component of displacement in that direction. That's what that means. The component is dropping a perpendicular to that axis and taking the component of the displacement. So the component of the displacement in the direction of the force, looking for a color to draw it with, is right here, right? So this is d in the direction of f. So we would write the work, instead of d in the x direction or y direction, it's in the f direction. So the work is defined as f times d sub f. That is a good definition of work. Force times the component of displacement in direction of force. Magnitudes, they're both magnitudes. We can also write from the second definition that is also equal to, and we'll see in a second why this is true. Well, actually, no. Let me, getting ahead of myself. Before I use that second definition, let's just see what d sub f is. D sub f is f d cosine theta. It's magnitude of f times the magnitude of displacement times the cosine of the angle between them. Because d cosine theta is the component of d in the direction of f, where theta, this is what's really important, is the angle between d and f. It's not the angle that it makes with an x-axis or y-axis, so you got to be careful of that. It's the angle between d and f. Really important to remember that. Theta is not the angle we make with some arbitrary axis, it's only the angle between d and f. So this is a good definition of work. Work is the magnitude of the force times the magnitude of the displacement times the cosine of the angle between the force and displacement. Now let's just show how that is also equal to this. And that is the magnitude of displacement times the force and direction of displacement. Hopefully you can already see that just says, if I want to take the component of force in the direction of displacement, I have to put an axis along the displacement, drop a perpendicular from the force, and I know it's kind of hard to see in this case, drop a perpendicular, and so the component of force in the direction of displacement, which we can call F sub D. F sub D, it's a better picture. F and D, and then just take the component of F in the direction of D, that's right here, we can call that F sub D. And that gives us the work, which I said is the magnitude of D times the force in the direction of D, F sub D, right? The force in the direction of D, D direction, not X direction, not Y direction, but the D direction. And that component is, FD is F cosine theta, where theta is the angle between the F vector and the D vector. So that is equal to D, the magnitude of the displacement, times F, the magnitude of the force, times the cosine of the angle between F and D. And you can see that those two give the same answer, that the work is always the magnitude of the force times the magnitude of the displacement times the cosine of the angle between them. So let's just look at the definition of work. Each definition is as good as the other. You can remember any one or all of them. The work done by a force, not the total work done, but the work done by a given force, is the magnitude of the force times the magnitude of the component of displacement in the direction of force. Or it's the magnitude of the force in the direction of displacement times the magnitude of displacement. Or it's the magnitude of the force times the magnitude of the displacement times the cosine of the angle between them. That's what all three of those mean, the same thing. And for those of you who have taken enough math, you know that this is what's called the dot product, F dot D. F dot D simply means what we just showed. I want to take a little aside and talk more about the dot product.